All right, let's talk about the invisible wall that the entire AI industry is starting to hit. And here's the twist. It's not about a lack of processing power. Nope. It's something much, much deeper, and it is costing an absolute fortune. Okay, let's dive right in.
So for the longest time, the logic was pretty simple, right? If you want a more powerful AI, you just throw more hardware at the problem. More GPUs, more servers, bigger and bigger data centers. It makes perfect sense. But what if that fundamental assumption, that core belief, is starting to completely break down?
Well, guess what? It is breaking down. This graph tells the whole story. You see, for a long time, as systems got bigger, the cost for each little bit of performance went down. That's exactly what you'd expect. But we've crossed a tipping point. That orange line shows the cost is now curving up, and it's curving up fast. We are literally paying more to get less. That right there is the scaling paradox.
So we're staring right at this thing called the scaling paradox. Why is our old, reliable strategy of just piling on more hardware suddenly failing us? Let's get into it. Here is the absolute heart of the issue. The bottleneck has moved. It used to be all about raw compute power, how fast a single chip could crunch the numbers. But now, with tens of thousands of processors all trying to work together, the real limit is coordination, just getting them all to work in perfect lockstep harmony. It's not about how fast the runners are anymore. It's about whether they all leave the starting block at the exact same millisecond.
So, coordination is the big problem. But what's causing that coordination to break down? It's time to pull back the curtain and unmask the real culprit behind this whole mess.
And here it is, the culprit's name, interconnects. The best way to think about the interconnects is as the central nervous system of an AI supercomputer. It's not the processors themselves, the brains, but the incredibly complex, high-speed fabric that weaves all those brains together into one single, cohesive mind.
Okay, here's an analogy that makes this crystal clear. Picture a massive, sprawling airport. The jets are your super-fast GPUs. That's your compute power. But the interconnect, that's the air traffic control system. Now, if that control system can't perfectly coordinate every single takeoff and landing, it doesn't matter one bit how fast your jets are. The whole airport just gets congested and grinds to a complete halt. This table really just nails the paradigm shift we're living through. In the old world, we obsessed over compute, measured in flops, basically just raw number crunching speed, and we kind of assumed every part worked on its own. But in this new world of massive scale, it is all about the interconnect. The bottleneck is now communication and synchronization, because everything is so tightly coupled. A tiny problem in one place now becomes a huge problem for everyone. And this brings us to the really strange, almost spooky part of this whole story. See, interconnect problems, they don't look like normal computer failures. They are much, much sneakier than that.
Yeah, we're not talking about a server crashing with a loud alarm and a big red light. Instead, the system suffers from what are called soft degradations. Think of it less like a car crash and more like a slow, silent leak in a tire. The system is still running, no errors are flashing on the screen, but its efficiency is just quietly bleeding away.
This diagram, the failure envelope, helps us visualize this bizarre problem space. You can see how as you increase factors like the sheer size of the system or mix in different types of hardware, you move deeper into this overlapping storm of quiet problems, things like silent degradation and straggler cascades. It's not one single bug, it's a whole environment of instability.
So what's actually lurking inside this envelope? Well, you get performance that just evaporates with no obvious reason. You get straggler cascades, where a handful of slow components can drag the entire multi-billion-dollar system down like an anchor. You can even have whole groups of processors that just drift out of sync with each other. It's truly the ghost in the machine.
So, how in the world do you fight a ghost? The short answer is, you don't. You can't. You need a totally new way of seeing the system. This is the real turning point, where we have to shift our entire perspective from looking at individual components to looking at the overall structure. And this image says it all. On the left, that's the old way of thinking. A simple, neat, layered stack of components, easy to understand. But on the right, well, that's the reality. The operator graph view shows the system for what it truly is. A dense, complex web of interconnected nodes where absolutely everything depends on everything else. Seeing the system as a graph isn't just a different diagram, it is a fundamentally different way of understanding where the real problems live. And this quote just gets right to the heart of it. System behavior comes from the interactions between the parts, not from the parts themselves.
In that graph we just saw, the connections, the structure, actually matter more than the individual dots. This mind-bending concept is called non-local coupling, and this diagram shows you exactly how it works. A tiny little hiccup on one single node doesn't stay local. No, it ripples out through that interconnect fabric, creating scheduling problems and delays in places that are far, far away from where the issue actually started. It is the butterfly effect, but for supercomputers.
Okay, so we've wrapped our heads around the technical problem, but what does it all mean for the bottom line? Because let's be clear, this isn't just some engineering puzzle. This is a massive, massive economic problem. Just look at this timeline. The green blocks are the compute phases. That's the good stuff, where productive work is actually happening. But all those orange blocks, those are sync phases. That's when the entire system is just sitting around, coordinating and waiting. As the system gets more unstable, those orange blocks get bigger and bigger. Costs are racking up, energy is being burned, but zero useful computation is getting done. That is pure, unadulterated waste.
And that waste isn't some abstract number on a spreadsheet. It has real, tangible, and painful costs. It shows up as having to rerun jobs over and over because they fail for no clear reason. It forces companies to over-provision, buying millions of dollars in extra hardware just to have a safety buffer. It's massive amounts of energy being wasted on idling parts, and it's countless engineering hours spent chasing these ghosts in the machine.
So if you remember one thing from all of this, let it be this. Interconnect instability is not a technical bug that you can just find and patch. It is an economic outcome that is baked into the very structure of our current large-scale systems. Which leaves us all with a final, really critical question. The race to build bigger and bigger AI is accelerating every single day. But as we build that future, are we actually focusing on the right things? Are we just counting processors, or are we asking the really hard questions about how to build systems that can scale not just in size, but in a way that is stable, efficient, and ultimately economically sustainable?